Okay, Chemistry 3111. This is Chapter 22, which deals with the chemistry of amines. And if you go way back to your days in general chemistry, the first amine or the first nitrogen-containing compound you probably learned about was ammonia. And amines are nothing more than derivatives of ammonia. So by now, everybody in the class knows the structure of ammonia. Here's the Lewis structure. We know NH3. When we see that, we're dealing with ammonia. And again, amines are just derivatives of that little compound, ammonia, and they can be classified as either primary, secondary, or tertiary amines. If we have one R group, we call that a primary amine. So if we wanted to write a condensed structure, it would look something like this. If we have a secondary amine, it's when we have two R groups, so we would put R2NH. And if we have three R groups, that's a tertiary amine. It's important to not mix up, let's say a tertiary amine with a tertiary alcohol, right? Because if we take T-butanol, which is a tertiary, this is a tertiary alcohol, the fact that the alcohol is classified as tertiary is based off of the alpha carbon, right? So we know that alpha carbon is attached to 3 carbons, and so we call that a tertiary alcohol. Whereas when we're classifying amines as primary, secondary, or tertiary, it's based on the substitution on the nitrogen atom itself. With that in mind, you should be well aware of the fact that naturally occurring amine compounds, or compounds that contain nitrogen-containing compounds, are called alkaloids. For example, here we have morphine, and it's got kind of an interesting history that it's named after the Greek god Morpheus, which is the god of dreams. Then we have cocaine, which is isolated from the leaves of the coca plant, and I'm sure you've all heard of that before. And then finally, nicotine, an addictive and toxic compound that's found in tobacco. And you hear about all these different things on the internet where people say, oh, this food is only one step away from plastic, or just crazy things that don't make any kind of sense when you learn a little bit about chemistry. But you guys all know what an acetyl group is. So everybody knows that when you have a methyl ester like this, that's an acetyl group like that. So if you replace the two hydroxyls that are on morphine, if you replace both of those, with an OAC, so if you replace both of those with an acetyl group, then, my friend, you would have heroin, okay? So you can see that there's not that much difference in the structure of heroin comparing that with morphine. And then you could even compare that to codeine, and you could go look that up. And codeine is very closely related to morphine and heroin, and codeine is found in cough syrups that you can purchase probably over the counter. Anyhow, there we go. So I'll erase the heroin thing. And just to, kind of put this bug in your ear, I mean, cocaine that is snorted on the street is not snorted like this. It's snorted as the hydrochloride salt, so it's a white powder, right? So, and the reason it, crosses the mucous membranes in the nose is because it's going to be soluble in there because it's delivered as a salt. Now, when you freebase it, that's when you make crack. But that's when you treat the hydrochloride salt with sodium bicarbonate in some kind of solvent, maybe water or ether or something. Anyhow, I don't know. I haven't made any crack. All right. Anyhow, let's see here. You guys have probably heard of neurotransmitters, maybe in biology class. Some naturally occurring amines are vital to neurochemistry. Here's the structure of adrenaline, which is responsible for the fight or flight response. Also noradrenaline and dopamine. And you can see how these compounds are all closely related. And you might have heard of, this compound that if I draw, something that's very similar to these, okay? So if I put a hydroxyl group down here and then an N-methyl like this, okay? Well, this is the structure of, and I don't show the chirality of this, of the chiral centers here because there's a chiral center. There's a chiral center here and here, but these are ephedrine would be ephedrine and pseudoephedrine, which are found in antihistamines. And if you take that and you reduce it, you can make this compound here. And this is methamphetamine. So this is methamphetamine, which is what is found in crystal meth, right? Anyhow, something interesting there. All right. Well, let's talk a little bit more about amines in terms of their basicity. It says here the trigonal pyramidal nitrogen atom of an amine carries a partial negative charge on its lone pair. Now, way back in general chemistry and in this class, we talked about molecular geometry. So here's the Lewis structure of this is called trimethylamine. If you look at the Lewis structure of that compound, we have, you know, one methyl group here in the back. We have one coming out in front like this. So it's got that trigonal, right, a trigonal pyramidal structure, which you should all be fully aware of. But if you look at the electrostatic potential map shown right here, you can see that all of the electron density, or the high region of electron density, is found in the middle, found on that nitrogen. And so the lone pair is available to function as either a base or a nucleophile. And at the very beginning of this chapter, we're going to talk about the lone pair functioning as a base. But most of this chapter, in fact, probably 75% of this chapter, is based on looking at the nitrogen of an amine behaving as a nucleophile. So the first box shows it reacting as a base with hydrochloric acid to produce a hydrochloride salt. And then the second reaction shows it functioning as a nucleophile in just a regular old, just a good old SN2 reaction right here. It's reacting with methyl chloride, and we're doing just a methylation on the nitrogen. So again, you need to be fully aware that the nitrogen of an amine can function as a base or as a nucleophile depending on the situation. Well, before we can really get into the nitty-gritty on amines, we have to talk about how we would name amines. And the good news is if you understood nomenclature and other chapters, you can borrow a lot of those skills to help you to name amines. And I'll tell you, frankly, when it comes to naming primary amines, and that's where we're going to start, is talking about just naming primary amines. Primary amines, their nomenclature is pretty much analogous to that of alcohols. Right? So if you understood how to name an alcohol way back at the beginning of Chemistry 3111, then naming a primary amine isn't that much of a stretch. Secondary and tertiary amines, a little bit trickier. But primary amines, the first rule is we name the alkyl group ending in "il," followed by the suffix amine. Now, this is how we name amines that have simple alkyl groups. So this is really only used for amines with simple alkyl groups. And in fact, all of these names that you see here, we have an ethyl group, an isopropyl group, and a cyclohexyl group. So we would call these amines ethylamine, isopropylamine, cyclohexylamine. These are common names. Okay, these are all common names. If you were to name them using the IUPAC or the systematic name, you would name it as the first one as ethanamine. You'd name the next one as 2-propanamine, and you name the next one as cyclohexanamine, because you would just name the longest carbon chain and follow it by amine. Okay, so you're not treating it like an alkyl group. Okay. And if you need some help on that, I could write those down here. So the first one would be ethanamine. The second one would be 2-propanamine, and cyclohexanamine would be the last one. Cyclohexanamine. And you're like, well, these look pretty similar. But again, when we're dealing with simple alkyl groups, common nomenclature is definitely going to dominate. If you have a more complicated primary amine, and this is what I was getting at, we call those alkanamines. If I go back here, we call these ones alkylamines. So maybe I could write that in here. So the common nomenclature, we call these alkylamines. That's where we name the alkyl group. If we name it as an alkanamine, it's a little bit different. In that case, we name them the same way that we did alcohols, right? But we use the suffix amine instead of -al. So you have this big compound here. The same rule applies as with alcohols, where we name the longest carbon chain, and we sought to give the functional group, the hydroxyl alcohol functionality, the lowest possible number. The same thing applies for an amine. You can see that we have 7 carbons in the longest carbon chain, and we want to give the amino group, that amine, we want to give it the lowest possible number. So we're going to start numbering 1 on the far left. So this is going to be a 2-heptanamine, or you could call it, the other way of naming it, if you called it a heptane 2 amine, that would work as well. Either one is perfectly fine. But first, you would have to designate the stereochemistry of the 2 chiral centers, and you should be able to do that. And then, of course, you would list the 2 methyl groups. We have one here, and then we have another one here. Anyhow, we're going to get some practice on nomenclature in just a second. A little more about nomenclature. If the amine is in a compound that has a functional group that has a higher priority, and you can see that I included a little bit of the order of precedence. Okay. We don't cover the order of precedence in gross and dirty detail in this class, but basically, for this chapter, whenever you have an oxygen-containing functional group, it's going to have a higher priority than an amine. Okay. In fact, the amine is going to be lower than anything except for a halogen, basically. In that case, you use the term amino for the substituent. So if we look at this compound on the left, the longest carbon chain has 1, 2, 3, 4. It's got a hydroxyl, so we're going to name it as an alcohol. And if you didn't have this group over here, that would be butanol, wouldn't it? So this is 4-amino-butanol, and then we have para-amino benzoic acid shown over here, right? It's para because the 2 groups are 1, 2, 3, 4 carbons apart, like that. Okay, what if you have a derivative of aniline? Well, when we have an amine directly attached to an aromatic ring, I taught you this a long time ago, that we call that aniline. So here's the structure of aniline. And the second compound here, you could call that metachloroaniline. When we name something as an aniline, we assume that the carbon that has the amine on it is going to be carbon number 1. So you could name the second compound metachloroaniline, or you could call it 3-chloroaniline. Either one would be perfectly reasonable. The next example, we take a look at this and we see that we have 2 groups on it, don't we? We have a fluoro and we have an ethyl. Well, remember that you're going to, whether you name it clockwise or counterclockwise, has nothing to do with tallying up numbers or locants for each substituent. All you're going to do is try to give the first substituent the lowest possible number. If I number going counterclockwise, the fluorine gets the number 2 and the ethyl gets the number 5. That's the correct way, right? If you were to name it, or number it rather, going clockwise, the ethyl group would have the number 3, and 3 is higher than 2, and therefore that would be the incorrect way to number that compound. So here's the correct way, just like that. There are multiple methods for naming secondary and tertiary amines. Like I told you, primary amines is pretty reasonable. If you understood alcohol nomenclature, usually students can get that down pat pretty quick. But when it comes to naming secondary and tertiary amines, things get a little bit trickier. There's a couple of options. When we're dealing with simple alkyl groups, and if you're like, well, Mr. Dion, what do you mean exactly by simple? How do I know when it's simple? Well, if it's something that you recognize, like an ethyl or a methyl or a propyl, right, or an isopropyl or a tert-butyl, things like that. In that case, you're going to name the alkyl groups, and you're just going to follow them up with the word amine. You use di and tri if there's more than one of that same group. If you have 2 groups or 3 groups that are different, you're going to follow alphabetical order. Take, for example, the compound on the far left. We have an ethyl group, we have a methyl group, and we have a propyl group. We list those groups in alphabetical order: ethyl, methyl, propylamine. The next one, we have 2 ethyl groups, so that's simply diethylamine. And the last one is triethylamine. Trimethylamine. Triethylamine would be this, wouldn't it? This would be triethylamine. Okay. Anyhow, there we go. All right. Now here's where it gets way more interesting. If you have a secondary or a tertiary amine, but we can't name it just using the simple listing of the alkyl groups followed by the word amine, right? We see that we have a methyl group here. That's pretty abundantly clear, as well as the ethyl group. But all of this down here, that's not as abundantly clear, is it? Well, in that case, it says you're going to find the carbon parent chain and use the suffix amine. The smaller groups attached to the amine should be named as alkyl groups with an N-locant. So this is something that's going to be brand new to you. And since the methyl group is attached to the nitrogen, we call it an N-methyl. The N is almost always italicized when you're reading a book that's printed. You don't have to obviously italicize the N when you're writing it out with your pencil. And we have the ethyl group, which is attached to a nitrogen, so that becomes an N-ethyl. These are alphabetized not by the letter N, but by the letter of the alkyl group. And then the rest of the compound is going to be named using the same old rules that we did before. We're going to name the longest carbon chain, which has 6 carbons in it. So this is going to be some kind of hexane derivative. It's got the amine on the 3rd carbon, so it's a hexane amine, or a 3-hexane amine rather. And we're going to list all the other substituents. We've got 2,2-dichloro, right? Chloro is going to come before N-ethyl, and then N-ethyl is going to be followed by N-methyl, right? All 3 of these substituents are simply listed in alphabetical order. Okay, remember, we ignore prefixes like di, tri, so on and so forth. And then, of course, since we have a chiral center in the molecule, you're going to put the stereochemical designation at the very beginning of the name. Well, that's a lot of information. And I think the best way to cement our knowledge in what we just talked about would be to try some practice problems. Assign a name for each of the following compounds. Remember, there's always more than one way to name an amine. We always want to go with the simplest possible way of naming an amine. That's usually the best thing you can do. Now, the easiest way to name this first amine would be to name it as an alkylamine, right? Because I have a methyl, and I have a cyclopentyl. These are all groups that you can recognize, can't you? Methyl, and cyclopentyl. And so remember, we ignore all prefixes except iso, cyclo, and neo. And so cyclopentyl is going to come before dimethyl, won't it? So the name of this compound would be cyclopentyl dimethyl amine. Now, there is another way to name this compound, and I haven't looked at the solutions manual to see how exactly he names it, but there is another way to name it, right? If we name it based off of the longest carbon chain, which is the cyclopentane ring, well, in that case, this would be some kind of cyclopentanamine, wouldn't it? And we have these 2 methyl groups on it, so it's going to be an NN dimethyl, right? This is an N-methyl, and this is also an N-methyl. Since there's 2 of them, we don't list N-methyl, we call it NN dimethyl. So that's something that I didn't go over with you yet, but you list the nitrogen for each time you have an alkyl group. So how would we put all that together? This would be NN dimethyl cyclopentane amine. All right. The next one, let's just look at the nomenclature in terms as of alkylamine, because we have 3 alkyl groups that are easily recognizable. They're all ethyl groups. Can anybody suggest a name for this compound? It's an amine with 3 ethyl groups attached to it. Yeah, exactly. It would be triethylamine, wouldn't it? So we would call this triethylamine. If you wanted to name this as an alkanamine, and I don't even have this written in my notes, and I usually write everything in my notes, you would never do that. Okay, you would never ever do this. In fact, if you walked up to a chemist in a lab and said, "Hey, do you have a bottle of NN diethylethanamine?" The person would look at you like you're crazy. So let's just leave it. Let's just keep it simple then. Okay, the next one, we find the longest carbon chain, which is the cyclohexane ring. Okay, so this is some kind of cyclohexanamine. We've got an isopropyl on the third carbon. So we go 1, 2, 3 like this. So this must be some kind of 3 isopropyl propyl cyclohexane amine. Okay, it's neat enough to read it, I guess. Now we need to assign the stereochemistry at the 2 chiral centers, don't we? There's one on carbon number 1 and there's one on carbon number 3. So this is going to be 1 something, 3 something, right? Well, could anybody tell me what the stereochemical designation is at the first carbon, the one with the nitrogen on it? I'll just ask you that one to start with. I think that one's the easier of the two. Anyone? Okay, well, we have a hydrogen in the back. Yeah, somebody said S. I would agree with that, right? We have a hydrogen in the back. The nitrogen is going to be highest. The nitrogen's going to be highest priority. The hydrogen's going to be lowest. Carbon number 2, the one that's labeled number 2, that's going to be second highest priority, and this one's going to be third highest priority. So we're going in counterclockwise direction, and so this is going to be 1s. If we look at the other one, erase some of this spinach here. Okay, we have a hydrogen going in the back, like this. If we look at these carbons, this one is attached to carbon, carbon, hydrogen. This one is attached to carbon, hydrogen, hydrogen. And this one here is attached to carbon, hydrogen, hydrogen. And so the number 1 priority is actually going to be the isopropyl group. So this will be our first priority. The hydrogen is obviously lowest priority. If we keep going out from there, hopefully you can see that this carbon is attached to a nitrogen. So this is going to be second highest priority. And then third will be like this. So we're going in this direction, which is clockwise. And so the third stereocenter is 3R. Okay, there we go. So we named the compound 1s3r, 3-isopropyl cyclohexanamine. All right, let's try some where we draw the structure of the compound. I find these are a little bit easier, maybe an order of magnitude simpler. The first one is tricyclobutylamine. Well, that means we're going to have 3 cyclobutanes attached to a nitrogen. So we'll draw 1, we'll draw 2, we'll attach them to a nitrogen, and then we're going to need a third one. Like that. So that's tricyclobutylamine. The next one is 2,4-diethyl aniline. We'll start by drawing just the molecule aniline. We know that the nitrogen, the carbon containing the nitrogen, or the carbon with the nitrogen attached, is carbon number 1. So I could number going clockwise or counterclockwise, doesn't matter. I'll just do it like this. So on carbons number 2 and 4, we need an ethyl group. We'll put an ethyl group here. We'll put another ethyl group here. And the last one, there's some stereochemistry here. Well, in the interest of time, since I spent a lot of time going over the stereochemical assignments, last one, I think the easiest way to do these is to start with, it says 1R2S, 2-methyl cyclohexanamine. If I just concentrate on this part, 2-methyl cyclohexanamine, what's cyclohexanamine? It's cyclohexane with an amine, right? An amino group attached to it. Okay, what's 2-methyl? Well, it's a methyl group there. So if I take that compound and I start fiddling with the stereocenters, as a student, I think that's probably the easiest way to figure it out. Okay, and once you determine, the correct stereochemistry, you'll see that they're both going to be pointing on the same side, same face of the molecule, like this. Okay, so this is 1R2S. So this is the R stereocenter, and this is the S stereocenter. All right, again, in the interest of time, I'm going to move on to section 22.3, which is the properties of amines. We've looked at nomenclature and the introduction. Well, when it comes to hybridization, this is something that goes all the way back to the beginning of Organic Chemistry 1. We talked about the hybridization of commonly seen elements in organic chemistry, like carbon and oxygen and nitrogen. And the nitrogen atom in a typical amine, like most of the amines we've looked at this morning, is sp3, right? We have the trigonal pyramidal molecular geometry. We have a tetrahedral electron geometry, and that lone pair is in a hybridized sp3 orbital. The bond angles are a little less than 109.5 degrees, aren't they? And the reason why is because of the repulsion of the lone pair right, which isn't bonded, and so it's going to push those bonds down just a little bit. Maybe I should double-headed arrow. Put a one-handed arrow. Okay, the carbon-nitrogen bond lengths. I'll never ask you about that, but they're in between the length of a carbon-carbon and a carbon-oxygen bond. Anyhow, I'm not going to go over this question in detail, but it says here, under what circumstances would the nitrogen be sp2 hybridized? This is something that if you need to review it, you definitely should. And the answer to this is when we have an amide, right? We looked at this in quite a bit of detail in Organic Chemistry 1. I remember because I was there, okay? We spent a lot of time talking about why is this nitrogen in an amide? Why is it not sp3 hybridized? Why is it rather sp2 hybridized? So if you need to look that up, you can spend some time doing that. But of course, it's got something to do with the resonance structure. Okay, so I'll let you take a look at that if you need to. Nitrogen atoms with 3 different alkyl groups are chiral, right? They've got 4 different groups attached, 3 alkyl groups in a lone pair. So technically, they would be chiral, wouldn't they? But amines are generally not going to be optically active. Okay, and if you've never thought about an amine as being chiral, you know, it's something that we didn't really discuss a whole lot in the stereochemistry chapter. But if you think about it, look at this structure and look at the mirror image. They're non-superimposable, right? Those are 2 enantiomers of each other. And if you're thinking, well, dang, why didn't we talk about this sooner? Well, there's a good reason why. And again, it's because amines are not optically active. And the reason why amines are not optically active is because they undergo an inversion. It's called a pyramidal inversion or pyramidal conversion, which occurs rapidly. So basically, the nitrogen goes from sp3 hybridization through this trigonal planar intermediate, where the nitrogen is sp2 hybridized, and then it kind of flip-flop, right back and forth and back and forth. And so you end up with a mixture of both of these enantiomers. And so an amine is not going to be chiral because of that. And you can see that the activation energy isn't very high. And so that, again, is why we don't consider amines as being chiral. What about the solubility of amines? Well, there's some kind of rules of thumb presented on this slide. It says that amines with fewer than 5 carbons are typically soluble in water. Primary and secondary amines are unique because they can form hydrogen bonds between intermolecularly, right? If I have 2 molecules of a primary amine, they can hydrogen bond to one another. Whereas tertiary amines cannot do that, right? Tertiary amines possess no nitrogen-hydrogen bond. Now, there's 2 sort of trends that are exemplified on this slide. The first one compares the boiling points of propane, which is an alkane. So here we have an alkane, and then we have an amine, right? So that's ethanamine, and then here we have ethanol, which is an alcohol. So we're comparing the 3 of these. Now you can see that the boiling point of the amine and the alcohol, even though their molecular masses are all pretty close, you can see that the boiling point of the amine and the alcohol are significantly higher. Okay. Now the next trend you see is that the boiling point of the amine is significantly lower than that of the alcohol, or you could say, well, the boiling point of the alcohol is a lot higher. The reason why is nothing more than the ability of a nitrogen-hydrogen to form a hydrogen bond is there, of course, but its hydrogen bonding strength is not as great as the oxygen-hydrogen bond. And the reason why is because nitrogen is not as electronegative as hydrogen, right? Oxygen has an electronegativity of 3.5, whereas nitrogen has an electronegativity of 3. And so, yes, there's going to be a delta minus here and a delta plus here, but on the alcohol, the delta minus is going to be much bigger, and the delta plus is going to be much bigger. The bond is more polar, and so the hydrogen bonds are simply going to be stronger. The next trend that we see is with these 3 constitutional isomers. All 3 of these amines have the exact same molecular formula, but they have different boiling points, don't they? The first one, propylamine or propanamine, is a primary amine. Then we have ethylmethylamine, or you could call it N-methylethanamine. That's a secondary amine. And then we have trimethylamine. I don't know under what circumstances somebody would call this N,N-dimethylmethanamine. Maybe if they've had too many alkaloids or something. But anyhow, the reason why the boiling point drops is because of their ability to hydrogen bond, doesn't it? Right? We have two opportunities for hydrogen bonding here, don't we? We have two nitrogen-hydrogen bonds, whereas in a secondary amine, we only have one. And so that is why when we compare the primary to the secondary amine, the primary amine is going to have a higher boiling point, right? It's more intermolecular forces. It's going to take more energy to convert that from a liquid to a gas. Trimethylamines got a really low boiling point, 3 degrees Celsius. That means at room temperature, it's definitely a gas. And again, there's no nitrogen-hydrogen bonds in there to speak of, and so there's no hydrogen bonding that can occur. And there you go. The intermolecular forces are going to be nothing more than London forces. And so, yeah, it's going to have this low boiling point. All right, let's move on from there. Many small molar mass amines have unpleasant odors and can smell like rotting fish. You see two compounds here, putrescine and cadaverine, which are both found actually in rotting fish. And another one would be trimethylamine. Trimethylamine, which we saw on the last slide, smells like rotting fish, and it's a gas at room temperature, so it can, carry around and get in your olfactories, right? If you've ever heard of fish odor syndrome, this is a disease, and I guess it's a rare disease, but some people have it, where their bodies can't metabolize. They have a deficiency in flavin-containing monooxygenase 3, and so they lack that enzyme which converts the trimethylamine to an N-oxide. And I did mention an N-oxide maybe once or twice in this course, but when they're unable to do that, the trimethylamine builds up in the person's sweat, their urine, their breath, and so they have a fishy odor. Anyhow, I didn't even know about fish odor disease until I saw a documentary, or maybe a short documentary about it on TV or something. Anyhow, kind of interesting stuff there. Okay, so the next time you smell a fishy smell, you'll know where it's coming from. It's coming from a low molar mass amine. I told you that first we were going to look at the basicity of amines before we discuss them behaving as nucleophiles. And amines are stronger bases than alcohols or ethers. And the way that we measure the basicity of an amine is by examining the pKa of the conjugate acid. So an amine can be readily protonated by strong or weak acids. Here we're seeing a reaction between triethylamine and acetic acid, which is a carboxylic acid. It's not a strong acid. It's not sulfuric acid or HCl, right? But it's sufficiently acidic to fully protonate or almost fully protonate triethylamine. You can see the equilibrium is going to lie hard to the side of the products here. And we see that the pKa of the conjugate acid, this triethylammonium ion, is 10.76, so around 11. And again, remember, the equilibrium is always going to lie to the side of the weaker acid. So it's a good idea to have or it's useful to have a general idea of the pKa values of protonated amines. The good news is you don't have to memorize all that many, because if you look at this slide here, it has the pKa values of the ammonium ions of several amines. You notice that they're all in the same ballpark, aren't they? They're all kind of like, between 10 and 11, really. So they're all pretty much in the same range. They all have a pKa of around 10 to 11, something like that, whether it's methylamine, ethylamine, so on and so forth. Okay, so again, it's a good idea for you to have this memorized, that when you have a simple alkyl group on your amine, that the pKa of the conjugate acid is going to be around 10. Okay, somewhere in that neighborhood, 10 to 11. And if you're wondering, why did you say simple alkyl amine, Mr. Dion? Well, the reason why is because when we look at the basicity of aniline derivatives and some other compounds, we're going to see that it's going to vary from here. Now, something that's important that you understand is that you can make the connection between basicity and the pKa of the ammonium ion. And that would be summarized like this. The higher the pKa of the conjugate acid, okay, means it's going to be a weaker acid, right? The higher the pKa is, the weaker the acid is. Therefore, you would have a stronger base. Okay? All right. Well, with all that in mind, let's take a look at the basicity of some aromatic aniline derivatives, some arylamines, and some heterocyclic amines. And you notice that the pKa of the arylamines on this side, okay, their pKa's are all around 5. So that means that they're stronger acids. That means that they're weaker bases. Now let's think about that. Why would, say, if we compare aniline, whose conjugate acid, this is called an anilinium, is 4.6. Let's go back and let's compare it to this, okay? Cyclohexylamine. The pKa of its conjugate acid is around 11, 10.7, close enough. Okay, let's draw it out here. If we compare these two, okay, they look pretty similar, don't they? There's a big difference. Okay, this is a stronger base than this. Why would that be? Think about it. What's basicity? Basicity is the ability to donate electrons, right? We think about Bronsted-Lowry definition of an acid and a base: proton donor, proton acceptor, right? And then we think of Lewis acid and Lewis base. A Lewis acid is an electron acceptor, and a Lewis base is an electron donor. So in terms of Lewis basicity, which one of these is going to be the stronger base? Well, of course, it's the cyclohexylamine, and the reason why is because these electrons that I'm circling in red, those are localized. They're stuck there, aren't they? Whereas the electrons in here are delocalized throughout this aromatic ring. And so they're just simply not going to be as available. If you look at the example of pyrrole, and we discussed this molecule chapter where we looked at aromaticity, the reason why the pKa of its conjugate acid is so low, the reason it's such a strong acid is because pyrrole itself is aromatic, isn't it? Okay, whereas this is non-aromatic. Okay, so when it's protonated, it loses its aromaticity, so it's really eager to give up that proton, and that's why it's a strong acid. Whereas pyridine is aromatic when it's aromatic or non-aromatic. Sorry, reading above. Whether it's pyridine or pyridinium, they're both aromatic, aren't they? And so the conjugate acid of pyridine is not going to be nearly as strong as the conjugate acid of pyrrole. All right, there we go. In general, amines that are more than 5 carbons are only going to be slightly soluble in water. The solubility is enhanced by the presence of aqueous acid because we get a protonated ammonium ion, which is a cation, and therefore it's going to be water soluble, right? We use this to help extract amines. This is something that was learned way back in Organic Chemistry 1 lab when we looked at extractions. It says here that amines can be extracted from organic impurities by using an aqueous acid, right? These two bullet points tie together. If you have a mixture containing, let's say, an alcohol, and an alkane and an amine, how would you separate the amine from the alcohol and the alkane? You would react it with some hydrochloric acid, right? You wash it maybe with 1 molar hydrochloric acid. Then you're going to get what? You're going to get the ammonium salt, right? You're going to end up with the ammonium ion. That's going to be soluble in water, whereas the alkane and the, alcohol, they won't be protonated, therefore they will remain in the organic phase. Pretty cool, huh? You can see how a solid understanding of acid and base chemistry can be helpful to purify organic compounds like amines. Anyhow, this next slide goes into even more detail, or sorry, where is it? I guess I threw this in here. It says here, many pharmaceuticals contain 1 or more amine functional groups and are marketed as salts. Yeah, many drugs are marketed as salts. You can see here we have a compound that's used to treat hypertension, or Gleevec, which is marketed as methyl sulfonate, right? And then you see here Viagra is marketed as a salt as well. Anyhow, that's all I really wanted to say about that. I think I kind of threw that in there as an afterthought some semester. The pK of most alkylamine conjugate acids is between 10 and 11. We already covered that. Arylamines are less basic, and therefore their lone pair is delocalized. The delocalized is lone pair is less available for protonation. Therefore, it's going to be a weaker base, right? Nothing more than that. Okay. Now, as far as those amine or those aniline derivatives go, and we already looked at these, right? We already looked at the pKa of the anilinium ion. Well, what if they have electron withdrawing groups or electron donating groups? Okay. Well, what's going to happen is, remember, the basicity is all due to the availability of these electrons, right? These electrons, right? How available are those? Well, if you have an electron withdrawing group, like a cyano group, that's electron withdrawing, and so that's going to pull those electrons even more into the ring. So they're going to be less available. It's going to be a weaker base, and therefore the conjugate is going to be a stronger acid. Okay. If you have an electron donating group, like a methoxy, this lone pair is going to be even more available than it was in aniline, and so the conjugate acid is going to be weaker. All right, there we go. So that's a lot of talk about acidity and basicity, and I think we kind of wrap things up here. Yeah, we're going to do a couple of questions in a second here. Again, the lone pair on an amide is not considered to be basic or nucleophilic because it's delocalized. In fact, if you look at the electrostatic potential map of an amide, you see that most of the electron density is actually up on the oxygen. And so again, that's why that nitrogen is definitely not going to behave as a nucleophile or as a base. At physiological pH, and this is going to be important in biochemistry and in the chapter that we look at amino acids and proteins and peptides. So physiological pH, amines exist primarily as ammonium ions. Recall that the Henderson-Hasselbalch equation can be used to calculate the ratio of the amine to the ammonium ion at a given pH. I'm not going to ask you to use that formula to calculate anything, but you should be able to, or you should understand where the Henderson-Hasselbalch equation comes from, because everybody who's in this class passed general chemistry too. All right, well, let's take a look at some practice problems. The first problem says rank this group of compounds in order of increasing boiling point. Yeah, these compounds are all constitutional isomers, aren't they? Anyhow, the first one is a tertiary amine. So we have a tertiary amine, we have a primary amine, and we have a secondary amine. Well, the highest boiling point is going to be the primary amine because it's got more opportunity for hydrogen bonding. So highest boiling point. The lowest is going to be the tertiary amine because it cannot hydrogen bond. Lowest boiling point. So we'll put here cannot form H bonds in a pure sample. Cannot H bond, and then the primary amine and the secondary amine can both hydrogen bond, but the primary amine has more opportunities for hydrogen bonding because it has two nitrogen-hydrogen bonds. Next ones are about water solubility of amines. Identify whether each of the following compounds is expected to be water soluble. What was the rule that we said? Compounds that have more than 5 carbons are going to be slightly soluble. Here we have 8 carbons, right? There's a total of 8 carbons, so we're going to say no, will not be water soluble, and we'll say since it's got 8 carbons. The next one we have isopropylamine. That's definitely going to be soluble. Yes. We'll say since it's only got 3 carbons. And the last one has a total of 6 carbons, so you might have a knee-jerk reaction to say, oh, it's going to be insoluble in water, but it's got 2 amino groups. So the ratio is, we're going to say the answer is yes, it will be water soluble. And it's because the ratio is that we have less than 5 carbons per amino group, okay? And if you wanted to just say, well, for every amino group, there's 3 carbons, so that would be akin to what we saw in B. That would be a perfectly legitimate rationale as well. It would be the same rationale. 22.6, let's try a couple of these in the interest of time. For each of the following pairs of compounds, identify which compound is a stronger base. If we look at the first one, A, if I label these as A and B, who could tell me which one of these would be a stronger base? I'll put in the lone pairs while you're thinking about it. Another way of asking this question would be saying, which one of these molecules, lone pair on the nitrogen, is more available? Open for business. Which one? Would it be A or B? Yeah, Sean says A, and he's correct. The answer is this one. It's going to be a stronger base. And the reason why is because the lone pair in the second one is delocalized, isn't it? Right? So it's simply not going to be as available because it has this resonance structure where the electrons are not on the nitrogen. The second one, if we look at B, we have pyrrole. We have the lone pair here, right? We know that pyrrole is a very weak base. Why? Because it needs this lone pair in order for the compound to be aromatic, right? Whereas the lone pair on this compound, this is an aromatic compound. It does satisfy Huckel's rule, but this lone pair is not participating in aromaticity. Okay, and so the answer is this one is going to be the stronger base, something like that. Rank the following compounds in terms of their increasing basicity. Remember, this is how available are the lone pairs on the nitrogens. We could draw them all in. How available are they? So if I label these, if I label these as A, B, and C, who could tell me which one of these is going to be the most basic? Does anybody have an idea which one would be the most basic, A, B, or C? Yeah, it's going to be C. C would be the most basic. Most basic. Right. The reason why is because methyl groups are electron donating. Okay. Which one of these is going to be the weakest base? Well, it's going to be B. This one is going to be the least basic. Why? Because aldehyde is electron withdrawing. And the bromine is electron donating by resonance, but it's also electron withdrawing by induction. And so since this one has an electron withdrawing group on it, it's definitely going to be the least basic. So that's kind of the rationale you use to solve problems like that. Okay, let's switch gears and get into some synthesis. We've got 2 hours left, so let's hit it. We'll start by reviewing some ways that we've learned to make amines. We have actually talked about a few ways that we can make amines in this class. The first one is preparing an amine from an alkyl halide. You can take and make a primary amine from an alkyl halide in a two-step process. The first step would be to displace the halogen of an alkyl halide with cyanide as a nucleophile. And so you could draw out the cyanide polyatomic ion, which looks like this. And then we could draw the curved arrows where we just displace the bromine like that. Then we end up with a nitrile. Remember, when you put cyanide in an organic compound, this is called a nitrile. And then we reduce that nitrile using lithium aluminum hydride, or you could even use hydrogenation to reduce that. But what do you do here? You end up changing this carbon skeleton, right? You don't want to forget that the carbon skeleton is expanded by one carbon. If you look at the first molecule, you have 1, 2, 3, 4, 5 carbons, but now you've got 1, 2, 3, 4, 5, 6 carbons. So you want to keep that in mind when you're trying, or maybe trying to apply this this as a synthetic strategy for preparing a primary amine. You can also prepare an amine from a carboxylic acid, and we looked at many ways to make carboxylic acids. And again, you probably remember this sequence where we take a carboxylic acid. In the first step, we treat it with thionyl chloride, that's SOCl2, and then we have to use excess of the amine. And the reason why we need excess is because when we do the nucleophilic acyl substitution, we form HCl. And so the second equivalent of the amine reacts with that HCl and converts it to a hydrochloride salt. Then once you've formed the primary amide, so this is a primary amide, you can reduce that with lithium aluminum hydride followed by treatment with water. Remember, with lithium aluminum hydride, the second step is always going to be water or a little bit of aqueous acid. Okay, well, with that in mind, let's look at another way that we learn to prepare a primary amine, namely preparing aniline. And we discussed nitration in the electrophilic aromatic substitution chapter. We talked about when you mix nitric acid and sulfuric acid, you make a nitronium ion, and how the aromatic ring can act as a nucleophile, and the nitronium is an electrophile. They react, you form the sigma complex, and then you end up with nitrobenzene. And that nitro can be reduced a couple of ways. You can either reduce it using simple hydrogenation with hydrogen in a catalyst like platinum, palladium, or nickel, or you can treat it with a different holy host of possibilities here. And I looked at this in the book. He lists a whole bunch of different things here. Now, just treating it with iron, zinc, or tin metal and HCl or H3O plus, we've already seen those before, but this is something new. Okay, the treatment of a nitro group with tin 2 chloride, that's new. And if you're wondering, like, why do we have to learn another reagent? Well, I don't know, to make life interesting, I guess. The reason why they throw this in here is Mr. Dion has used tin 2 chloride. I'm trying to think. The reason why you would use tin 2 chloride, I think, is because in some cases, if you have something that's going to be so easily reduced, the tin 2 chloride is just milder. You know, it's a milder reducing agent, nothing more than that. Okay, but those are the kind of little tidbits that I find, like the MCAT or the DAT or the ACS. They love to bring up all those little, nuances that you learn in organic chemistry. Okay, it says here to draw the structure of an alkyl halide or a carboxylic acid that might serve as a precursor in the preparation of each of the following amines. We'll start with A. Let's imagine we're on a quiz here. You want to make this compound, which is 1-butanamine. You've got 1, 2, 3, 4 total carbons. If we wanted to make this from an alkyl halide, doing an SN2 with sodium cyanide, we'd have to start with one less carbon, wouldn't we? So instead of 4 carbons, we'd only want 3 carbons. And so if we started with 1, 2, 3 carbons and then an alkyl halide, I'm going to choose iodide. High roller, iodides are expensive. The first step would be to treat that with sodium cyanide. That would give me 1, 2, 3, 4. And then I'd have my nitrile on there. So let me count this up. 1, 2, 3, 4. Yeah, that's right. Okay. And then in the next step, I would treat that with lithium aluminum hydride followed by H2O. And then that would give me 1, 2, 3, 4. Boom. That would give me my desired product like that. So that's making it from an alkyl halide. If I wanted to make it from a carboxylic acid, remember that strategy involves a primary amide, and so we would have the same number of carbons. So if I wanted to make this from a carboxylic acid, I'd start with butyric acid, right? In the first step, I'd have to treat it with thionyl chloride, SOCl2. That gives you the acid chloride, doesn't it? Right? Next, we're going to treat it with excess ammonia to give you the primary amide. I'm not going to draw that. Once you've got that primary amide, you can reduce that the same way that we reduced the nitrile. Treatment with lithium aluminum hydride followed by treatment with water. And that will give you the product. Okay, let's try, I don't know, let's try the second one and then we'll move on. I'll give you a second to look at the second one. I'll give you a minute to look at it and think about it. Okay, so if I wanted to make this from an alkyl halide, again, I'd want to start with one less carbon. You can see that we have 1, 2, and then the aromatic ring. So I would want an aromatic ring plus only one carbon, wouldn't I? And then I'll use the bromo. So this is benzyl bromide. We would treat that with sodium cyanide. In the first step, that would give us this compound. And then in the last step, I'm going to treat that with lithium aluminum hydride, followed by an aqueous workup, and that's going to give me the desired product. If I wanted to make it from a carboxylic acid, I'd start with the correct number of carbons. So I have 1, 2, and then I'd have my carboxyl group here. We'll just draw everything out here. In the first step, we're going to treat it with vinyl chloride. Second step, we're going to treat it with excess ammonia. That would give us the primary amide. Then we're going to reduce that with lithium aluminum hydride, and then follow that with an aqueous workup, and that will give us the final product. The last question is very much in the same vein as the first two, and so we'll move on from there. Then we'll talk about some new reactions. Section 22.5, preparation of amines via substitution. Amines are great nucleophiles and readily undergo SN2 substitution with an alkyl halide. If you take ammonia and you stir it in the presence of iodomethane, which is shown here, methyl iodide, right? You see the beautiful SN2 reaction, and then that gives you this quaternary ammonium salt. The quaternary ammonium salt undergoes a proton transfer, and then we end up with a primary amine. The thing is, now you've got an alkyl group on here that's electron donating via hyperconjugation. And so that's going to render the lone pair on the nitrogen even more nucleophilic. Let me show you what happens. That reaction that we saw on the first slide to make this compound, it's actually really difficult to do it just by combining ammonia and methyl iodide. In fact, I'd say it wouldn't work. I mean, you would get some of the product, but you'd end up with such a mess that you would just be banging your head against the wall. And the reason why is because what I just said. After you alkylate, once you install that methyl group, it's going to be like a runaway train. It's going to do it again, followed by a proton transfer. It's going to do it again, followed by a proton transfer, and it's going to do it even again. So it doesn't stop until it alkylates 4 times, and you get a quaternary ammonium salt. This is called exhaustive alkylation. You're like, yeah, it is exhausting. Anyhow, well, that's what it's called. And so it's not an effective way to make a primary amine. So basically, what I'm getting at is that this reaction that's shown here, where you take ammonia and you make a primary amine, pretty useless, okay? Because what's actually going to happen is it's just going to keep reacting like shown over here, and you're going to end up with this. That's not a primary amine, is it? No, far from it. So it's just like those infomercials, right? There's got to be a better way, to get orange juice from this bag of oranges than, throwing them against the wall. And one of the best ways to make a primary amine is to do what's called the azide synthesis. I worked with a guy for a long time who was a real expert in azide chemistry and diazochemistry. Azide synthesis, brand new synthesis for you guys. It's the conversion of an alkyl halide to an azide, followed via an SN2, followed by the reduction to yield a primary amine. So you should be able to draw the Lewis structure of sodium azide. The azide anion looks something like this. Okay, I drew this with GenChem 1 just the other day. Anyhow, so here's an azide ion, right? That can act as a nucleophile. like this and displace the halogen. So then we have the azo compound, or the azide, I should say, and then you can reduce that a couple of different ways. You can reduce it either using hydrogenation or reduction with lithium aluminum hydride. Both work perfectly well. This is a better way to make a primary amine than trying to monoalkylate ammonia. And here's the mechanism of that reaction. Now, I only drew this step right here. But then when you treat that with lithium aluminum hydride, you're going to reduce this nitrogen here, and then it undergoes the loss of a leaving group, and that leaving group is nitrogen gas. And so the last step is when you add the water. So the first step is, right, sodium azide. I got sodium amide on the brain, don't I? Okay. The second step is lithium aluminum hydride, and then the third step is to treat it with water, right? And that does a proton transfer to give you your amine. All right, Gabriel synthesis. A new kind of synthesis to make a primary amine. The reason why, we learned the Gabriel synthesis, I think, is because making azides is cool. Like if we go back here, making azides like this, it's okay, but I think they're probably explosive, so I don't like to mess around with anything that's explosive. When I interviewed with potential supervisors in graduate school, one of the guys I met with, his name was Sandro Gambarata, and he was an expert in explosives and all this stuff. And he said, if you join my group, you'll learn how to handle dangerous chemicals. As soon as I heard that, I said, nope, no thanks. So no desire to handle anything dangerous. Not fun. I don't want to lose my fingers or something. Anyhow, the Gabriel synthesis is another way to make a primary or a secondary amine from phthalimide. So here's an interesting compound for you. That's a mouthful, right? I guess you guys look at phenolphthalein in general chemistry too. But here we have phthalimide. So first you convert phthalimide into an anion with potassium hydroxide. So we get potassium phthalimide. Now I'd have to look this up, but I think you can buy potassium phthalimide. But if you look at the solutions manual in the textbook, every Gabriel synthesis always just starts with phthalimide and then a deprotonation. Maybe it's because he wants you to understand, he just wants you to learn, and he's just trying to get you to realize, okay, well, it's just going to be a simple, just a simple deprotonation like that. And I've got two lone pairs. And the pKa of that proton, you think about it, that's kind of similar to, what is the diethyl malonate that we looked at in the last chapter. I think the pKa of that proton is probably around, probably lower than 9. It's probably around 8, something like that. Anyhow, and then the pK of water is 16, right? pK of water is 15.7 is what it says in our textbook. And so that's going to completely deprotonate that, right? You get this doubly stabilized phthalimide. And then you're probably thinking, well, that looks like it could be a really nice nucleophile. Yeah, you'd be 100% correct if that was your train of thought. So potassium phthalimide can then serve as a nucleophile, and it can be alkylated. You can look at it either way. You can say it's a nucleophile, and it's doing an SN2 with an alkyl halide, or you can say it's alkylated. Anyhow, so we end up with the alkylated species, and you're like, that's not a primary amine, okay? That's not a primary amine, Mr. Dion. Where's the primary amine? Well, the good news is that you can take this intermediate and you can blow it apart and get the alkylamine. Now, this is something I don't think I've ever done in my life. Okay, I don't think Mr. Dion's done a lot of reactions, tens of thousands. I don't think I've ever done Gabriel synthesis. If I did, I must have blocked it out of my memory. But as far as I know, we got two ways of breaking it apart. It says the last step generally employs aqueous acid or hydrazine. You guys remember hydrazine, right? That's NH2, kind of rocket fuel, right? The last step generally employs aqueous acid, so H3O plus or hydrazine, to liberate the amine. Okay, so you got two options, right? Option number one is to treat it with aqueous acid. You end up with this dicarboxylic acid. This is phthalic acid. Okay, so that's one idea, and there's no problem with that. It's probably okay, but you end up with an ammonium, so then you'd have to treat it with sodium hydroxide in order to get the free amine. Another thing is, I think, and I could be wrong, but I think that this is slow. I think that's kind of a slow way of doing it. And so if you treat it with hydrazine, NH2, NH2, it's like a nucleophilic acyl substitution, and you end up with the uncharged amine. I've taught this class long enough that I've given enough paper quizzes and seen what my students, gravitate towards. And I'd say it's probably most students just choose this hydrazine because then they end up with the amine right away, and they don't have to memorize. Okay, well then I've got to wash it with a base or something. Okay. Anyhow, kind of cool. So we could even write here just as a reminder. Let's write here uncharged amine or free amine. Okay, let's use a Gabriel synthesis and show how we would make each of the following compounds. Okay, the nitrogen, if you think about the Gabriel synthesis, let's back up. The nitrogen comes from potassium phthalimide, doesn't it? Come on, Mr. Dion. Where were you? There we go. So use a Gabriel synthesis to show how you'd make each of the following compounds. So that means we're going to have potassium phthalimide, aren't we? We're going to have to make it from phthalimide. So that means we're always going to start with this compound, right? We're always going to start with the phthalimide. Looks like this. Deeper, not a lot of space here. But anyhow, it looks like that. Okay, so all of the syntheses are going to start with that, right? If we started with that molecule, I'll draw it out maybe a little clearer here. My 5-membered ring with my nitrogen in it. We start with this. What's the first step going to be? Okay, the first step is to convert it into the salt. So that means treatment with potassium hydroxide, KOH. Okay, maybe I'll just draw out all the steps for the first one. What's that going to give me? That's going to give me my potassium phthalimide. So we'll draw that out. Okay, now that I've got this, I'm going to react it with an alkyl halide in order to do my SN2 reaction. Did anybody name the alkyl halide you're going to react it with? Well, you're going to react it with cyclopentylmethylene iodide, chloride, or bromide, right? So let's draw that out. So we would react it with this compound. We'll choose the bromide. That's going to displace it like this. And then we're going to end up with this intermediate. Let's draw the intermediate. And again, it's not asking us to draw all these intermediates. I just find that it's easier to understand organic chemistry if you don't have to memorize or just blindly memorize everything. If you have an idea of what the heck is going on, right? And then the last step is let's just treat that with hydrazine, right? That's going to blow it apart. Okay, give me a thumbs up if you follow me on the Gabriel synthesis there. Anybody there? All right, got one person. Okay, you got 2 people. Great. All righty. Well, there we go. Let's try the last one. Remember, the only thing that's going to come from the phthalimide is the nitrogen. That means that what we're going to do is we're going to start with phthalimide. In the first step, we're going to treat it with potassium hydroxide. In the second step, we're going to treat it with this compound where we've got the 2 aromatic rings. And we have this secondary alkyl halide. I'll choose a bromine. And then in the last step, you're going to treat it with hydrazine. And that's going to give you your product. And that's the Gabriel synthesis, just like that. If I can make a recommendation before coming to class on Monday, I highly recommend reading the rest of the chapter, starting with section 22.6, which deals with reductive amination. It's a very important reaction in organic chemistry. I know I say that about all reactions, don't I? But we've got that to cover. Then we have 22.8, 22.9, Hoffman elimination, nitrous acid reactions, diazonium ions, and azo coupling. So we still have quite a few more reactions to cover. And then we're going to basically skip the section on heterocycles, and that'll be it. So there we go. So quite a bit more to cover on Monday. So I recommend reading it ahead of time so that you can, be well prepared for the quiz on Wednesday.